Okay, thank you very much. I hope everything is functioning here. I'll try to function. And before I start to function properly, if you have any questions left over from yesterday, please let me know. For example, now. Okay, because there have been some questions that we discussed right after the talk yesterday. Okay, so here is just a quick reminder of the basic properties that I want to use in order to compute the slices. And in Paul Arne's talk this morning, you have seen that this computation of the slices might actually be interesting. And as usual, I forgot something. So I said I have sort of the forgetful map from Hermitian to algebraic K-theory, the hyperbolic map from algebraic to Hermitian K-theory, and the properties these compositions satisfy. And then I had to have a certain co-fiber sequence, which is also familiar in topology, the Wood co-fiber sequence, multiplying by eta. This element already played a prominent role in the first two talks this morning. The cone on eta on Hermitian K-theory is precisely algebraic K-theory, and the connecting map is then the hyperbolic map. I forgot one thing, and this is the periodicity that Hermitian K-theory satisfies. Algebraic K-theory satisfies a 2-1 periodicity, which is apparent from the description of the P1 structure I gave. Remember, it was the same space every step. This was not visible for KQ, but in fact this is, since it's its birthday, I should say this is Karoubi periodicity, right? So there is a 8-4 periodicity for Hermitian K-theory. And instead of beta, maybe I call this gamma to distinguish. Yeah. And okay, I already started drawing a picture here. So this picture gives a description of the slices, and the picture is of course misleading, as all pictures are. So this here continues infinitely to the left. This here is a copy of an integral Eilenberg-MacLane spectrum sitting in the appropriate bi-degree. This here gives you the slice and then also the weight that you have to suspend this with. And this here then gives you the simplicial degree when you add the weight to it. Okay, and these ones are mod 2 Eilenberg-MacLane spectra. So this means that every slice of KQ is an infinite sum of Eilenberg-MacLane spectra. Yeah, it's a sum of all these guys on this line. And these colored arrows, I'll explain that later. This depicts the first slice differential. And you can see from what I wrote here, or you can guess from what I wrote here, that certain Steenrod operations come up. Yeah. I'm not giving you the differentials. I'm here giving you the slices, and then I give the map from one slice to the suspension of the next. And each summand might map to several summands in the next slice. This is what happens. Yeah. I might get back to this picture, but first I would like to play around with these relations a little. Using as input the computation of the slices on algebraic K-theory. Okay, here's a lemma which you get from the first two compositions. If you compute the effect of this composition on slices, this is multiplication by 2. And if you compute the effect on the other composition. This depends. This is 2 if n is even, and it is 0 if n is odd. This you basically get fairly directly. Yeah, maybe. Of course, you have to check what happens with epsilon. And oh yeah. Oh, what is this? Okay. Sorry. Yeah. Yeah. Thank you. Okay. This is basically a computation that Voevodsky did. If you look at the permutation on the Tate motive Z of 1, it's the identity. Yeah? And this here was induced by the permutation of the 1-1 sphere. So if you permute that, you get a -1 because there's a 1 sphere implicitly inside it. So this gives us that this map here on slices is -1 for all n. And that proves the first thing. And the other thing, that the stable Adams operation psi -1, this on slices gives -1 to the n for all n. And this comes from the fact that when you shift it by sigma to 1, you get minus psi -1, not psi -1. And this can easily be derived from the model of algebraic K-theory I have given. So this gives us this lemma, and now we know the slices, but we sort of have to know the starting point. And actually, when I mentioned the slices of K-theory, which have also been mentioned this morning, I forgot to mention one thing. So we have the sphere spectrum, and algebraic K-theory is a ring spectrum. It comes equipped with a unit map. And this is factored by the forgetful map. And this here was computed to be motivic homology, HZ, but this here is the same. So this map here is an identity, the unit map. And this means that the zero slice of KQ contains HZ as a direct summand. And this is our starting point. So this we know from the start, and what is going to happen now is that I will use this lemma and the wood co-fiber sequence a few times, about 4 times, to make some deductions about the slices. And when I've done this 4 times, I'm through because of the 8-4 periodicity. And then I will derive a certain formula for the slices of KQ, which is a slightly incomplete formula. Okay, why does this work? This works because if we take the wood co-fiber sequence and the zero slice, this is a triangulated functor. So I get another triangle. And here I have the zero slice of sigma 1, 1 KQ. But this is the same as the -1 slice. As the 1, 1 suspension of the -1 slice of KQ. Because of basically the construction of the slice filtration. So the next step I can also write down as sigma to 1 of the -1 slice of KQ. And this here I can accordingly write as sigma to 1 of the -1 slice of KGL. And this here is then sigma to 1 of the hyperbolic map on the -1 slice. Yeah. And what I can deduce from the fact that this here is the projection is that this co-fiber sequence sort of splits. This here is the zero map, so this here is actually the zero map, and I have identified this M as the 1-1 suspension of the -1 slice of KQ. It's not really much of an identification, but at this stage. But let's continue. So when we want to compute the 1 slice of KQ, I take the wood co-fiber sequence, and this here in the same fashion is then the 1-1 suspension of the 0 slice of KQ. And here we already know something. Yeah, we know that at least we have one copy of motivic homology sitting inside there. So this gives us our starting point, and the thing we have to check now is what actually this map here does. We know what this here is. This is a 2-1 suspension of HZ, and this is a 2-1 suspension of HZ, and a 2-1 suspension of this M. And we have to be able to describe the map in order to compute this here, and the lemma over there basically tells us that this map here is of the form 2, 0. You have the 2 here because this composition here is always because this composition here is 2 on the even slices for K-theory, and this gives us the 2. And we have the 0 here because what you can deduce from the lemma is that this M here satisfies that 2 is 0 here. Because we have the 0 here and the multiplication here. So this is what the lemma gives us, and this means that we have a computation of the first slice of KQ. So this is a 1-1 suspension of a mod 2 Eilenberg-MacLane spectrum, and we have the rest here. Okay, and we keep on going. And I should say, this of course uses the fact that the slice filtration is a triangulated filtration, unlike the Postnikov filtration in the classical stable homotopy category, which is not triangulated. It's a T structure, but not a filtration by triangulated subcategories. Okay, 1 slice. So now I have to write down the 2 slice. Oh wait. Okay, we know what this here is. This is a 4-2 suspension of an integral Eilenberg-MacLane spectrum. And here, oh, now I'm bound to get confused with degrees here. This we have somehow identified. And again, the lemma serves to compute that this here is the 0 map. I mean, this is the sort of the first hyperbolic map on the hyperbolic map on the first slices. So as a computation we get here for 2 suspension of HZ, and then we have a 2-2 suspension of HZ mod 2, and we have this part M, this which we don't know really, and yeah, I can do it another time, yeah, for S3, and then this integral guy which sort of be reduced to a mod 2 guy again, and maybe I'll just write this down. So this would then be a 5-3 suspension of HZ mod 2 and a 3-3 suspension of HZ mod 2 and a 3-3 suspension of this M, which we don't really know. But the thing we can use now is the periodicity for KQ. So this is the same as the third slice of the 8-4 suspension of KQ. And this here is the same as the 8-4 suspension of the -1 slice of KQ. But the -1 slice, this is basically M. So this here is the same as the 7-3 suspension of the -1 slice of KQ. No, wait. No, sorry. The 7-3 suspension of M. So what we see, what is contained here in this M as a direct summand, is a -2 0 suspension of this here and a -4 0 suspension of this here. Yeah. So this is contained in M. Yeah. So we have a 1-3 suspension here and a -1-3 suspension here. It's contained in M. Yeah, and this keeps on going. So we get this infinite sums. Yeah? And this sort of gives the following description. Let me just write it down for the 0 slice of KQ. We have HZ, and then we have an infinite sum of evenly suspended mod 2 Eilenberg-MacLane spectra, and we only identified these as direct summands. There might be something else, and being a student of Waldhausen, I want to call this mysterious summand mu. Yeah? And the theorem will follow when I show that this mu is 0. Is this what I'm going to do next? Maybe. Yeah, maybe. Okay, so mu is the mysterious summand, and the lemma is that mu is contractible. This is what I have to prove, and then I have some computation of the slices. So maybe I don't want to prove this right now, but I rather want to make a small turnaround and connect this with Paul Arne's lecture a little. You may wonder, in the case of algebraic K-theory, the slices looked exactly as the homotopy groups of the corresponding topological spectrum Ku. And if you look at this infinite sum, and you recall what are the coefficients of topological Ko, there are no infinite abelian groups coming up there in the coefficients. Yeah, the coefficients of Ko, they look much smaller. Why is this so big? Yeah. Maybe this is also mysterious, and I can explain this a little by connecting with what Paul Arne explained. He discussed the canonical map you get from KQ, which is the fixed points of a certain C2 action on KGL, to the homotopy fixed points. Okay, so we have this map, and this map, well, it's not always an equivalence. You need some conditions, but it's close to being an equivalence if your base field has a finite 2 virtual cohomological dimension. Characteristic 2 is forbidden anyhow. Then this here is an eta completion. And then there are conditions telling you that the eta completion is actually the same as this here. For example, if the field has finite cohomological dimension. Yeah? For example, for finite fields, we know that these two things are the same, and this in fact can be derived probably from Friedlander's computation already. He computed Hermitian K-theory of finite fields of odd characteristic. Why am I saying odd? Ah, yeah, I remember now. Okay, so these things are closely related. They're not quite the same. And now we can sort of dream a little. We know what the slices here are. We have this involution on KGL. And now let's just look at the zero slice of KGL, which is an Eilenberg-MacLane spectrum. And since we have an involution here, we also get an involution here. But as you can fairly easily compute, there are only two possible involutions on this P1 spectrum. It's the identity involution and -1. And we can sort of dream that we can exchange slices and homotopy fixed points, although this is not true, as Paul Arne mentioned, in general. And we can try to compute the homotopy fixed points. Let's say we take the trivial action. And this is in fact what will happen on the even slices. Yeah? On the odd slices we have the non-trivial action. And when you compute the homotopy fixed points here, this is similar to what you can compute in topology. So what you will get is actually an infinite sum, precisely of the form given above. And this is because the computation of the homotopy fixed points uses a free contractible C2 space, just a space. And in fact, if the involution is trivial, we just have to smash with the classifying space of C2. And this is RP infinity. And since we have sort of a linear situation here with motivic homology, this can be computed as this sum. This is sort of some heuristic argument why such an infinite sum does not sound so unreasonable after all. Any questions? Okay. Shall I write down the homotopy fixed points for the non-trivial involution on HC? Okay. So that's -1. And this. Yeah. Yeah. I mean, thinking of a space as a motivic space is, you can think of it as a triangulated functor, so it respects co-fiber sequences, it respects weak equivalences. Yeah, this is sort of the right adjoint to the constant motivic space functor, and this can be quite mysterious. No. No, it's more subtle than that. So if you take the right adjoint of the I don't know what it is, but it's gigantic, right? I mean, I think Joseph Ayub worked on this. Markus, do you know? Of the Betti realization. Okay. Okay. Sorry, then I take this back. I'm confusing the two things here now. Yeah. Okay. Sorry. Yeah. Okay, there's an equation sign with just one thing on the left hand side. I have to complete this. All right. Okay, so this is the situation if the involution is non-trivial. But this was just sort of some heuristics. I should prove this lemma that this mysterious summand vanishes. And fortunately, Jens explained certain things this morning. I'll recall these things. The first statement, which is maybe not... maybe before recalling this, maybe I should make a precise definition. The P1 spectrum is cellular if it is contained in the localizing full subcategory of the stable homotopy category over some base S generated by just the spheres. So this, yeah. Oh, so it's not. So that it's a triangulated full subcategory. It's closed under retracts, and it's closed under arbitrary direct sums. So this basically means everything you can build out of spheres using a homotopy co-limit. Yeah? This is what this localizing means. And this is usually the point, when I explain this is where the algebraic geometers safely fall asleep. Yeah, because no reasonable, interesting algebraic variety is cellular. Of course, there are some. Yeah, but the majority of these do not seem to be cellular. Of course, you can start with elliptic curves. Yeah, of curves of positive genus. They are not cellular. But the thing is, the cohomology theories we've discussed so far, which is, of course, the sphere spectrum is cellular, KGL is cellular, also the motivic cohomology spectrum is cellular. I have to watch out a little about the characteristic, but in characteristic 0, the integral one is cellular, and over a field of positive characteristic, it is cellular if the characteristic is invertible in the coefficients of the Eilenberg-MacLane spectrum. What did I forget? KQ, right, KQ. Here's a fact, and this is the fact that Jens also mentioned. KQ is cellular no. One model I gave for the space was that it's just the infinite Grassmannian. Yeah, and the finite Grassmannians are the sort of prototypical example of cellular varieties. I can also give you another argument, if you like to see that. And no, maybe you don't want to see it, but I would like to give it. Yeah. Let me give you another argument. Let's agree that the sphere spectrum is cellular, okay, and also projective spaces are cellular. So also then infinite projective space is cellular. Yeah. So for algebraic K-theory we have a Snaith model, which is due to Gebner, Snaith, Spitzweg, Ostvaer. But of course I can continue if I like. I can think of P infinity as being the Thom space of the universal, sort of the tautological line bundle on the corresponding infinite Grassmannian parametrizing line bundles. This area is cellular, and the same holds for the tautological line bundles on the higher Grassmannians, and these build up the algebraic bordism spectrum MGL. This is cellular. And then we have Landweber exactness. KGL is the same as MGL, where you quotient out a bit. So inside of here we have the generators of the Lazar ring. And let's just kill x2, x3, and so on. And let's invert x1. And these are sort of cellular constructions. Probably the geometric argument is better, right? Okay. Okay. And actually, what is the reason why it is also true for KQ? And there we actually use the Panin-Walter model. And they use explicit Grassmannians, but then for sort of symmetric forms. I think they call them quaternionic Grassmannians. But they explain the cell structure of these varieties very explicitly, and it gives this fact. Okay. Now these cellular P1 spectra were mentioned by Jens in his talk because if you want to decide whether a map of P1 spectra is a weak equivalence, you would like to say, oh, it's an isomorphism on homotopy groups, so it's a weak equivalence. But this is not quite true, because I mean the generators in your homotopy category are not just spheres, but all smooth varieties. So the statement should read, a map of P1 spectra is a weak equivalence if it induces an isomorphism on presheaves of homotopy groups, where you enter not just spheres, but also smooth varieties. And in fact, since we use the Nisnevich topology, we can pass to Nisnevich sheaves of homotopy groups. But nevertheless, it's not just the global sections of these, not just the homotopy groups. But if the two P1 spectra are cellular, which means they are generated by spheres, then it suffices, of course, to evaluate on spheres. Yeah? So to just look at the actual homotopy groups. But this is not what I will use. Here is another fact. If E, let's see, is cellular, then its slices are also cellular in a sense, and in fact I would like to derive one consequence of that. if you have a cellular spectrum, it basically means that it has no interesting sort of variety direction, and the same then descends to the slices. Yeah, they are just basically given as I should write the Eilenberg-MacLane spectrum associated to a chain complex. Yeah, they are just given by a chain complex of abelian groups. And one other thing I could say here, these are just given by Tate motives, and in particular they are invariant under base change. Okay. So we want to determine the slices of KQ over a field, and then we can check a situation which might be easier, and this is usually the case when you pass to an algebraic closure. So we pass to a field which is algebraically closed, and then I'm going to use a theorem which was explained by Jens this morning in detail. They state it only for the complex numbers, but it's valid for any algebraically closed field. Which has characteristic different from 2. And then there's the sphere spectrum over this field. And here I invert, as Jens did this morning, the Hopf map on this spectrum, this P1 spectrum. And the homotopy groups as a bigraded ring are given by F2. We have, of course, eta. And I wanted to use different notation. What was the notation that Jens used? I think he had 9 and sigma. Modulo sigma squared. So the bidegree of eta is 1, 1. The bidegree of V9 is 9, 5. And the bidegree of sigma, which is this third Hopf map, is 7, 4. Yeah. And actually they state this after 2 completion. But the thing is, what is this ring an algebra over? You can take pi 0, 0 of this here, and by Morel's theorem, this is the Witt ring of the field, and the Witt ring of an algebraically closed field is just Z mod 2, which means that this guy here is 2 complete already. And so the computation, the 2 complete computation they make is actually an integral computation. And the consequence that Jens described is that and I also have sort of the similar description. If I define kW to be kq with eta inverted, then kW has a very small cell presentation. Over an algebraically closed field. It kills.
Because there are a lot of zero divisors.
Yes, it kills, but a lot or something survives as well.
But of course, you wouldn't invert it in this cost.
I mean, the thing is, and to a topologist it might sound surprising that something remains, right? Because if you invert the topological eta, you get the zero spectrum, because it's nilpotent. So motivically, of course, this does not have to be true. C2 equivariantly also something survives. Yeah. Yeah. Yeah, so this morning Jens mentioned Tom Bachmann's theorem, which states that over the reals, I mean, if you invert 2 as well in the motivic sphere, and you invert eta, then you just see the 2 inverted classical stable homotopy groups of spheres. And they are, of course, highly non-trivial. Okay. Let's see. What did I want to say? Okay, right. So here we have a small cell presentation. And this means that we can basically compute the slices. And now there's one thing that I wanted to mention already yesterday, but I did not. And this is actually, let me mention this now, nevertheless. So here's a theorem which is probably, I should attribute it to Levine, and he says it's due to Voevodsky. One can in fact compute the slices of the sphere spectrum. I already gave you the zero slice, which is the same as the zero slice of MGL for geometric reasons, and this is the same as the zero slice of KGL. This is just a motivic homology, but in general, the nth slice of the sphere spectrum is I'm sorry, I'm not good at memorizing things. I should be able to memorize this by now. I've seen it so many times. But still, where is it? I wrote it down somewhere. Ah, there it is. Okay. Let's take the sum over all integers, but don't worry, it's a finite sum. Yeah, it's a finite sum. And here I take 2n minus m suspension. This is the nth slice, so it has to have weight n. And then I take motivic homology with coefficients in the following abelian group. I take the integers tensored with a certain x group. And this is the E2 page of the Adams-Novikov spectral sequence. So we know that here, sort of, if we fix this n, we have only finitely many, and these are finitely generated abelian groups, and in fact, the only infinite abelian group is the one by degree 0, 0, which is the integers. The other ones are all finite. For example, the zero slice is HC. The one slice, this is a 1-1 suspension of HZ mod 2. And the 2 slice is a 2-2 suspension of HZ mod 2. And then it's a 3-2 suspension of HZ mod 12. And I could give you the 3 slice without looking, and maybe even the 4 slice. So the small slices are, yeah? Oh yeah, this is the co-algebra of co-operations of complex bordism. what is the name? The Weber-Novikov coalgebra? Is this the name? It's the Steenrod, the dual Steenrod algebra for this cohomology theory. Yeah. Right, right. Thank you. So this here is true after you invert the exponential characteristic. Of f. So this means it's 1 if the characteristic is 0, and it's just the characteristic if the characteristic is not 0. Yeah. So in characteristic 0 you can just take this as it is, and if you're in positive characteristic you have to invert the characteristic in here for the statement to make sense. Not to make sense, sorry, to be true, to be proven. It might be true in general. That's a general conjecture. Okay. Okay, so this is a certain algebraic object that may not be too familiar to you. It's not I'm not very familiar with it. But the thing is, we can describe elements in here. And the usual way to proceed is to fix a prime number and then look at Brown-Peterson theory instead of complex bordism. So then you write BP here, and there's a certain tradition on how to name elements. For example, I can state that this guy here, this is generated by alpha 1 at the prime 2. And this here is generated by alpha 1 squared. And this here is, in Ravenel's notation, I think alpha 2 over 2 bar. Yeah, generates a Z mod 4 in this thing. So you have actually a handle on the few slices. So this looks complicated. Let me write down something which is a lot simpler, and this is a corollary of this computation that Andrews and Miller make, and this is the slices of the eta inverted sphere. And since this is eta periodic, if I give you the 0 slice, I have given you all slices. Yeah. So I give you just the 0 slice, and this is an infinite sum. I take all natural numbers except for 1. And then it's, let me call these I. So it's an infinite sum of mod 2 Eilenberg-MacLane spectra. Yes. 0 is a natural number. Oh, yeah, certainly. The idea is actually very simple, because what you do is you resolve the sphere spectrum using algebraic bordism. So you have the sphere spectrum, you have MGL, you have MGL smash MGL, and this is, how do I have to write this down? This is some co-simplicial. It's the Adams resolution based on MGL. And, well, usually you take homotopy groups and get the Adams-Novikov spectral sequence for homotopy groups. Here, let's take slices first. And the funny thing, what happens with the slices, because sort of can control the slices here very well, is that the resolution computes the slices of the sphere spectrum precisely. It's not just the E2 page of something which computes the slices, it really stops at this point. It's very nice. Yeah. Computational, I don't.
Had you used a different resolution based on a different spectrum, you would expect the term to be X over the corporation of that.
This is true. I mean, of course, MGL is. I mean, it has the similar role as MU in topology, but its coefficients are more complicated because you also have Milnor K-theory showing up in there. But you see the Lazare ring as a certain diagonal in there. No, maybe I would like to, as before, have Marcus answer this question after my talk. But after my talk. Or do you want to answer it now? I thought after my talk. Yeah? Okay. Okay. Good. Okay, so of course you have to know the slices of MGL first, and this is given by basically the Lazare ring. Yeah, this is sort of the same formula where you place mu star here. This gives the slices of MGL. Okay, let's see. Here we have the slices of the eta inverted sphere spectrum, which uses this Andrews-Milnor computation, and this is over any field of characteristic not 2. And this efficient cell presentation, so if F is algebraically closed, characteristic not 2 gives us that the zero slice of KW is the sum over all integers and then even suspensions. Yeah. So the way that this cell presentation here is derived is that you kill sigma and mu9 is inverted, and if you kill sigma it means that you kill all the odd summands that are here. Yeah, every odd summand is sort of generated by a sigma times a power of mu9. So if you kill sigma, then you will get all the non-negative even integers, and if you invert mu9 you will then get the negative even integers here. And this here shows that the mysterious summand is contractible. Okay. It seems as if I have something like 5 minutes left. Is that... Yeah. Okay. So, in some sense, I have proven a theorem now which I didn't even state properly. The only thing I stated was this stupid picture with the colors. Yeah. Okay. That would end the section 2. Remember, I had 4 sections. Yeah. The third one would be the differentials, and the fourth one would be applications. So we have 3 options now. Either I say something on part 3 or something on part 4, or I stop here. Part 4. Okay, part 4. I have to say that I developed a kind of obsession with these slice differentials. Yeah, it's not healthy, but I really like to talk about them. I really like to talk about them. Okay, applications. Of course, what you get from this is a slice spectral sequence, and the disadvantage of this slice spectral sequence is that the first page looks so huge because you have this infinite sums coming up there. So you have to hope that these differentials do something good, and doing something good in this context here means killing elements. And this is what they do in specific cases. So here's a... Oh wait, here was also some... No, it's not. So section 4, applications. Okay, one can do computations. For example, take the ring of integers. in a number field. And one can compute KQ of this guy here, mod 2, say. And this is in fact been pursued by PhD student of Paul Arne. Did I write his name correctly? Okay. Okay. Pardon? Oh yeah. Two. Let's say two is inverted. Yeah. So. Yeah. Sorry. Yeah. Okay. Okay. I'm not saying that we can explicitly write down all the groups here, but I mean you can write down certain groups up to extension, and yeah, there are some pretty nice results here. I've been looking for a PhD student for quite a while now who wants to use this slice spectral sequence in order to compute something for, say, toric varieties. Let's see what's going to happen. And of course, there's one thing which is an interesting application. You can look at what this slice filtration does on sort of a very simple thing. You might wonder. So if I look at the homotopy groups of this P1 spectrum KW, I get Balmer's higher Witt groups. And if I take, so this means if I take the homotopy groups ST, this gives me the higher Witt group S minus T of the field, but they are all gone. So this means that there are, it's just the Witt group of the field if S is congruent to T mod 4 and 0 else. And you get a filtration on the Witt group, and this coincides with the fundamental ideal filtration. Okay, so the first page of this slice spectral sequence basically takes the mod 2 motivic homology groups. So this is my notation for mod 2, little h. And then I have, and so on. And this would be corresponding to the Witt group of F. And here I should have 0, but I have lots of terms coming up here. H01, here I have H12. And it's the whole upper half plane, which is filled with non-zero groups. Yeah? Oh yeah, it's the ideal of even dimensional forms. Yeah, you have a dimension map mod 2, and that's what it is. Yeah. Okay. Okay, and Milnor's conjecture is that if you take the associated graded of the Witt ring, then you get the mod 2 Galois homology of the field, which is also another Milnor conjecture, which is the same as the mod 2 Milnor K-theory of the field. And this is sort of what we see here, but we have lots of other chunk on the E1 page. So when we pass to the E2 page, all this chunk dies, and we get H00, H11, H22, lots of zeros here and there. So we get that E2 is E infinity, and this way we get a proof of Milnor's conjecture on quadratic forms. That sort of the associated graded of the Witt ring of a field is the same as the mod 2 Milnor K-theory. Pardon? No. Well, I don't know. But the methods we use start with the fact that we have a P1 spectrum which represents Hermitian K-theory. And this is not known. And I know that Marco Schlichting has been looking for this for at least is it 10 years or 15 years, or I don't know. Yeah. So characteristic 2. Yeah. It could all work out, but I don't know. Of course, then you would work with symmetric bilinear forms instead of quadratic forms, probably. Probably, because this is sort of what Morel's computation of the zero stable homotopy group of spheres predicts. Yeah, similar applications are, one can recover some theorems of Suslin on what the second symplectic K group of a field is, or the third orthogonal K group. So you can look at the slice spectral sequence, compute the E2 page, deduce that nothing happens there anymore, and you get some sort of known results this way. These are applications. And yeah, what I did not do is to compare this with sort of Bachmann's work on the very effective slice filtration, but my time is up, I guess.